And the next talk to be given by Jean-Michel Lamarre is on technical lessons learned from Planck for future space experiments.
Thank you. Can you hear me? So I have to speak here, I believe. Okay. Thank you. And what I'm asked to do is to speak of technical lessons for other and for future space experiments. And while listening to Yannick, I could not prevent myself of thinking how to project the various difficulties that we had to what he is going to face in the near years. But when I was preparing this talk, I thought it was a nearly impossible task, because you could spend a full conference on listing the lessons from the various aspects. And I spoke, hopefully I spoke with a number of people. I have to thank them. But I must admit that I have a bias. And I will speak of what I'm knowing the best. That's the HFI instrument. And I asked the LFI people to apologize, to restrict myself to what I'm knowing. When we are speaking to lessons, it's about the essential properties. And the essential properties of the instruments are in the case of Planck, where the sensitivity and the systematics. That's not very original when we just heard Yannick. What characterizes Planck is that the sensitivity that we had is near to the fundamental limits. That's the photon noise of the source itself. And if you want to do better, you have to either to have a larger number of detectors, or to have a mission that is much longer in time. And also, due to the fact that we have improved the sensitivity with respect to previous missions, we have been hitting new systematics. This we had to fight, and you will see that's not secondary effects. We had to fight systematic that on the signal were the main, or one of the main visible effects. If we want to classify the systematics, we have what are the additive effects, that signal that adds, that's a spurious signal that adds to what you observe, what is coming from the receivers. And you also have a kind of systematic, is that you don't know the real properties of your instruments. And you can make simulations, but if your instrument is not exactly what you think it is, your simulations just collapse, or you are wrong about. And you may also have systematics coming from the data processing. And I have an example here. I don't know if you can see the central part of this picture moving. It's a fixed image, and what you can see is the product of your brain and how your brain processes the movement of your eyes on the picture. And that's exactly what we can fear, and that's why the one part of the data processing, one important part, have been simulation, starting from the sky model, the Planck sky model that has been presented before, and it's a way to test, and every result, everything that we have done has been tested and must be tested and will be tested in the future. Now I'm coming to the additive systematics, and the most obvious that we had in the signal from the first day of the mission. It was the glitches on the signal coming from the cosmic rays. And we have anticipated that, because the receivers that were chosen, these are these are bolometers. At the left, you have a spider, the so-called spider web bolometer. It's 1 millimeter in diameter. At the center, you have the thermometer. And the grid that you see is the absorber for a wavelength larger than a millimeter or larger than a few hundred microns. It behaves like a metallic absorber, a continuous metallic absorber. But to cosmic rays, it offers a reduced cross-section. And that was the anticipation and the design measure that we have taken. And at the right, you see the polarization sensitive bolometers that are also have also a grid absorber. And when we looked at the signal of all the channels. And that's what you have. What? I don't know. If you want to have, which one is it?
It's the one. It's the one in the middle.
Okay, first.
So.
And when you look at this figure, these are all the channels, the high frequency channels here, 1 bolometer of each channel, and the low frequency where you see the dipole, which is the most obvious signal that you have, but you see the large number of spikes that you hear. This is 1 minute of signal because Planck is rotating on 1 RPM. And each of these glitches is something like that, with energy that is deposited immediately and with a relaxation with the time constant of the bolometer. But you see the large number of signals we had. And this, we have to throw away about 20% of the data to remove these glitches. And when this, at the beginning of the mission, the solar activity, the solar was quiet. And when the solar activity increased, the solar winds pushed away somewhat the cosmic rays, and the total number of data that was thrown away was going down to 10–15%. But it's not negligible. And you can think that if we had been wrong by a factor of 2 or 3, the mission itself could have been jeopardized. And when analyzing these glitches, you see that there are several families of glitches here. And we must admit that this was more than what we expected from the spider web design of the bolometers. And see here that the picture of the full picture of 1 bolometer, which is a polarization sensitive. Maybe you can see here the absorber wires here the thermometer. And you have, when you look at this picture, you have the answer is that part of the glitches are generated on this silicon support here. And you see that there are several ways in which the heat deposited by the leech can propagate through up to the bolometer here. One you don't see here, but you have some wires here supporting this bolometer, and one of the ways is ballistic phonons going from the silicon plate here to the thermometer here. Then the lesson from that are that we had designed the bolometers, but we had not tested them in a real environment. That's not an easy task to do that, but that was something that we should have done. And the environment of the bolometer is as important as the bolometers themselves. And we should be ready for if we have in future bolometer experiments to measure the CMB in space, we should be ready to remove a large number of such leeches, and we should be ready also to design bolometers in a better way to avoid this, to anticipate this question. Now I'm coming to the question of the instrument knowledge, which has occupied many people these last months and last years with the data. And at the beginning, with François Pajot in charge of the calibration, we had made a list of the different properties of the instrument and what should be calibrated on the ground and what could be known and will be best known from the flight data. And you see that the main beam, the far side lobes, spectral response, time response of the bolometers, optical polarization, linearity, absolute response, detection, and you see that most of them will result from a measurement in flight. So the ground calibration is mostly understanding how things are working and improving the preparation of the reduction of the flight data. But there are a couple of things that are the linearity issues and the spectral response issues that you especially for the spectral response issue, you cannot, you have not a spectrometer in flight. Unless you have, as one person in the science team has proposed, unless we have two instruments facing that you can intercalibrate with each other, and one including a source, and the other one having and cross-calibrating and doing two independent measurements. Now, for the linearity, part of the linearity will be, we are going to be able to measure it on the brightest sources, such as a planet for HFI, but also for LFI. And I'm coming here to the spectral transmission. Measuring the spectral transmission of an instrument with very cold detectors is nothing easy, both for both HFI and LFI. And you have here a tank, a vacuum tank, which is 1.5 meters in diameter, and with an external spectrometer, and you have to inject light here. That's something complex. And you get, in the case of HFI, you get a rather good measurement, and you see the kind of features that you have here. And when in flight you you see on the data that the CO lines of the interstellar medium are really important, you think that the measurement of the spectral response of the instrument in all the channels, you can see here where the CO lines are, and you think that the excellent knowledge that you have acquired on the ground will be the key for removing this effect from the dust measurement, and for maybe establishing the maps of the CO lines. And when you do that, it works, but it is in competition with mere component separation. And what I understand from the paper on the CO maps that you see here, that the component separation is a good solution, as good, at least as good as using the detailed measurement of each line here. And the fact that we had a template, an external template, to check, that we had an external template to check our results was of the really important in this case. For the LFI measurement, this is more difficult from one point of view, because within the same horn, the two polarization may have rather different responses. These are dBs, if I'm not wrong. So that's the bandpass mismatch that can be important both for LFI and HFI when we go to polarization measurement, may be a problem when you go to measure, to separate, to remove the foregrounds, and so on. Now I'm coming to the beams, and I will be not very long on the beam, just asking a question: are the mirrors good enough? And when you are using frequencies on 1.5 decade of frequencies, the answer is not an easy one. And if you see here some defects that are on the secondary mirror, and you see the imprints that you can see when you look a bright planet that you remove, but around the main beam you have this kind of things, you may think, and you are right, that this is too complex to have a fit with physical optic model, as WMAP did, and or LFI can do, but for HFI, it's too complex for that. Is it a big problem? Probably not. And here you have in all channels, you see that these spikes that we had around the main beam are at a level of minus 45 dBs or minus 50 dBs, and that's probably good enough, at least for the surface quality. But for the knowledge, it's something different. And the knowledge includes not only the main beam, but also the far side lobes. And these far side lobes could never be measured directly. We had no measurement on the moon, and that's a pity. We have to measure them by indirect methods. When I'm coming to the conclusion now, you see that I have taken a few examples, but something as a beam is essential for CMB experiment, because you are playing the whole calibration of the instrument with the beam. What the first thing is that the first lesson I take is that we must anticipate and minimize the systematics at the design level. It was done. For example, it was done for the 4K coolers and the mechanical microphonics that could be induced by the mechanical cooler. It worked up to a certain point, and we are still fighting with the residual of the systematic. And by the way, a lesson is that if we can avoid to have a mechanical cooler near to very sensitive detectors in the future, we must avoid that. In the case of Planck, it would have that would have meant that we had a big helium cryostat, and it was we had no solution for that. In fact, in the case of Planck, especially because we had the two technologies. The second point is that a global and detailed calibration strategy must be defined in advance, and that means that we must be able to anticipate on the data reduction process. And that proved to be difficult in the real life because the people in the data processing were telling, when we know what systematic effect you have, we know what we are going to do. That's not an easy game. You must take the opportunity to characterize and understand your instrument as much as possible when you have it on the ground, and it's a short period because it comes late in the game of the schedule. And you still are going to discover systematics in flight. Some of them may be difficult to understand. I think that there was a non-linearity issue that was taken for a gain variation for a long period due to the fact that we are calibrating on the dipole, and both could be, the effects were absolutely mixing. And the most dangerous systematics are those that are changing with time, and we had this problem with the 4K line of the mechanical lines spectrum of the 4K cooler. A word on the methods to correct systematics. Obviously, what is the most powerful tool is a redundancy, and the scanning strategy is essential. The template from other experiments was very useful, and also the fact that we had access to the raw data for both instruments, it was essential to understand what was happening and how to correct systematics. The numerical and physical models of instrument parts are also necessary sometimes. Last remark is the sensitivity is a key tool to measure, identify systematics. And at the end, if we really can find the good methods, we finish with systematics that are just comparable with the noises. If I want to conclude, is that the Planck was a risky mission because all the technology was really new, and we had technical challenges that In general, I think that we did well, even if we are not fully satisfied with everything. And there was a question how it is possible to make such a big and complex team work for years. And I don't have the answer. What I have is only that I'm amazed that it has been working as well, and that many people have spent a lot of energy for that. And what you can hope, Yannick, is you have as good people to help you around. Thank you.
Thank you, Jean-Michel. So, one or two questions? Yeah. This one.
Martin, this one's working.
This.
Yeah, I was particularly impressed by the emphasis you gave on having access to the raw data and not depending on data compression. I think this is a particularly important lesson that would affect Euclid, which was not mentioned before. If you're going to have 15 billion sources that you want to look at in a period of a few years, you're probably going to be heavily compressing the data on board. And I think this is a really dangerous way to proceed. One of the unfortunate things is that the space agencies have not been improving telemetry sufficiently in going to higher bandwidth over the years. It's an expensive process, but I think if we're going to have missions that are as ambitious as those that are mentioned here, you're going to have better telemetry, and that's a kind of investment that astronomers hate to pay for because it doesn't immediately translate into new knowledge, but it's a necessity, I think, in the long run.
I must tell that this remark is coming, the remark of the usefulness of availability of raw data came both from LFI and HFI teams, that we had, in real life, we had to compromise. That means that the data with which we are working for the what has been presented here is compressed data, but we had access to the raw data either by small chunks or for this that receiver only, and after this receiver only, or during the ground-based calibration. And this was essential, but I can tell you that if we could have had twice the telemetry rate, some problems may have been, if we had been clever in using that, for sure, may have been easier to solve.
Okay, one other quick question.
Sorry, I just want to point out for the LFI, I may speak for the LFI just, about the data compression. We did a very deep campaign, a very deep study, which lasts for 5 years roughly, to understand in the LFI how data compression works and what is the result and what is the effect on the science. with a lot of analysis, analytical models, test campaign. Also, for the LFI, and we publish the algorithm, so you may check what the algorithm is. Also, as has been explained, every day we receive 15 minutes for each channel in turn of uncompressed data, that is raw data, as they are collected by the LFI, and we do comparison with the output of the compressed data. That is, we have at the same time both data in both forms to check that everything is working good and it is within the specification. So I guess, and we did a campaign for the calibration of the compressor during the first light, or just before the first light, and a verification after the first light to check that everything is in shape, and the compressor is fairly robust, and we have been able to assess that the quantization noise introduced by the compressor is within roughly half of the RMS of the noise, and then you have to convolve. So the result is that the noise which is added by the compressor can be relevant for the single sample when observed as an example a point source, but when you pile up many observations, this noise becomes practically negligible, and we work a lot to be safe of that. Thank you.
Okay, thanks. Thank you very much, and let's thank Jean-Michel again for his talk. Okay, our next talk is by Paolo De Bernardis, who will talk about CORE, the next generation CMB space mission.
Thank you very much.